go over the ones that you canceled out? And the brown marker?
For here?
Yes.
The spring is just starting out initially just sitting there. It's not compressed or stretched. Technically, it's ideal. It has no mass in and of itself, and so even if it were oscillating back and forth, well, there's no mass attached, it would be oscillating back and forth infinitely fast. Tangent. But just picture the spring is just sitting there, so it's not compressed at all yet. And so that's why this is zero.
Oh, okay, I thought that they got canceled out by each other.
Oh, no, they don't get canceled out. They're knocked out for separate reasons.
Okay.
Just like over here, these two are knocked out for different reasons.
Okay, I understand now, thank you.
Okay. Other questions right now? Now recognize I can also make this problem a little bit more fun if I then said that how far up does that 15 kilogram mass move back up the ramp here? Because it comes down, collides, creates a 15 kilogram mass, it compresses almost 5 meters, and then it'll get shot back up. What's the conservation of energy problem again? Or, not that you're ready for it yet, but in a month you will be, add a little bit another twist to it by saying it now sticks to the spring and it will oscillate back and forth. How long will it take for that mass to oscillate back and forth? You'll eventually be there. You're not there yet. However, there is another part of the problem. Suppose the collision changed. It's now perfectly elastic. So we still have this, that hasn't changed. Then it comes down to which technique do you want to use. Oop, I erased the number I wanted. What was the velocity in the perfectly inelastic after the collision? How fast was it going?
5.715 meters per second.
7158?
No, just 715.
715. Okay. That's the perfectly inelastic collision velocity after the collision. And so we're going to take advantage of that. We're going to use technique number 3. So I've got my 5 kilogram mass here. I got my 10 kilogram mass here. And so before the collision, this one's going 17.146. That's going 0 before the collision. We need to shift into the zero momentum frame, so I'm going to subtract 5.715 from both sides. They collide, so we flip the signs. And then we shift back. And so this will be 11.43430, given the numbers that we have here. There is some rounding involved. Technically, in this situation, because this mass is twice that mass, this number right here should actually be the same as that number right there. If you don't understand why, it's not a huge deal at the moment, but if you do understand why, just recognize that if I just add them up, I get a 0 here, whereas before I had a 1. It's a rounding thing. And then here, when I subtract, I get negative 5.716. So the 5 kilogram mass collides and then bounces back up the incline. The 10 kilogram mass goes then shooting into the spring. And so we were back to the equation we were with before of 1/2 mass, this time it's the mass of the 10 times its speed squared is equal to 1/2 k delta x final squared. So this is 1/2 times 10 times 11.43 squared is equal to 1/2 times 20 times delta x f squared. Let's cancel out. So somewhere around 8 meters. I'm looking at Madison like it's a responsibility. What'd you get?
I'm not doing that, sweet. Oh, I saw. 8.0822.
Questions?
What do we plug in to get that number?
You get this number?
Yes.
Basically, it's that divided by 10,
Okay.
and then take the square root. Did you forget to take the square root? Was that a problem?
Yeah.
You get me it, Brendan?
Sorry?
Are you getting it?
Yes. Thank you.
Other questions? All right, I'll leave you with the following thought. If I've got this frictional surface here and a perfectly elastic wall. So if something bounces at whatever velocity, speed it hits the wall, it's gonna bounce back to the exact same speed. All the kinetic energy will be conserved. So this is some mass M, and I have another mass over here, mass M, heading right towards it. If the masses are the same, then what should happen in a perfectly elastic collision, because that's all that's happening in this problem, is this mass will come in, hit that, this one will stop, and that one will move on, hit the wall, come back, hit that, and then shoot back that way. So the number of contacts, there's 1, 2, 3 contacts, if the masses are the same. Anyone difficulty visualizing that there's gonna be 3 contacts? I'm gonna change the problem slightly, I'm gonna make this 10 times the mass. So what's gonna happen is this 10 times the mass is gonna hit it, it's gonna continue moving to the left, or your right, continue moving to your right. As this one hits the wall, comes back, hits that, and so the smaller mass is gonna bounce back and forth a number of times, and eventually it's gonna be enough to cause the 10 kilogram mass to be moving away faster than the other mass is moving. So in that case right there, if it's 10 times the mass, there are actually gonna be 31 collisions. Now let's make this 100 times the mass. Anyone see the pattern and guess how many times how many collisions there are gonna be?
301.
Ooh, not 301, wrong pattern.
310.
Nope, although you're closer.
311.
314.
Okay. I would've just kept going up.
Now let's make it 1,000 times. Anyone want to take a guess If you see the pattern, how many times is it gonna hit?
And numbers up.
It's gonna be 3,141 times. If we make it 10,000 times,
Yeah, 4.
5. 100,000 times,
9.
yes. What's the pattern?
5.
Yes. This is gonna be the relative masses here. So I guess what if I call that M1, M2? It's M1 over M2 times pi, rounded down to the nearest integer. So, and that's all the digits of pi I can remember, so that's why I stopped there. There's a video, a guy who does something called stand-up maths, S at the end of math, where he goes in, he talks about this. Oh, or is it might have been a different one. Anyway, I recommend stand-up maths. He does sort of math humor. I don't remember if he's the guy who did this one or not. Anyway, there is a reason why it does match out to pi, but we definitely don't have time right now, and it's not technically out of scope. But, so long, farewell. Oh! At least I organized these somewhat. Brandon. James. Let's stop.